Good afternoon, everyone, and welcome to another session of chemistry. I hope you're having a very good time, and I hope you're keeping safe. It's another day of learning of chemistry, and I appreciate God for keeping us alive. We'll try our best to to keep improving on a daily basis. One thing I want to encourage you is uh, make sure that you improve your chemistry knowledge every day. Even if you don't get to write your exam as soon as you're anticipating it, just don't give up. Keep learning chemistry. You'll never regret why you're having this or your encounter with me. Actually, I have to share one experience. I think I was in SS3 also when I had similar
Good
encounter.
afternoon, Mr. Nkwocha.
Good afternoon. How are you, Temilala? I had similar encounter too. I
I'm
met
fine,
one
thank you.
chemistry guru when I was in SS3, and since then, I don't think my life has been the same anyway. The first thing that happened to me was I appreciated how the man was digesting the chemistry. Let me say digesting the chemistry. He was really, really digesting the chemistry. uh, and I was impressed. I can't lie. And that actually sparked my interest in chemistry. So over the years, I've um, I've taken chemistry very serious. I can't lie. How will I say it? I've gained a lot of things learning chemistry, and also inspiring a lot of students to take up chemistry as a core. You know, recently I got a student of mine who is studying chemistry in university. I was like, "Are you serious?" About the subjects he had as option. What is it lesson? Yeah, go on. So of all the subject that the guy had as option when he was processing admission, he just felt that he was a little bit more comfortable with chemistry. So that was what led him to doing chemistry in school. Okay, so today we will not waste much time. We'll go straight to the business of the day. We start talking about organic chemistry part two, the various terminologies in organic chemistry. So we've talked about functional groups. All right, so we talked about the various examples of functional group where we can be classified. We talked about isomerism a lot. I actually appreciate everyone who contributed immensely to this isomerism lesson. So it's really awesome. All right, so we look at the various types of isomerism, and it was really an experience actually talking about isomerism online. So today, we'll not waste much of our time. We'll just go straight to alkanes. Now, I know a lot of students are waiting for us to get to alkanes, carboxylic acid, carbohydrates. Even me, I can't wait. But funny enough, you can never predict it. Your question can come from anywhere. And this is the backbone of organic chemistry, the alkanes. So if you're able to understand alkanes, alkynes, you'll be able to understand the rest of organic chemistry. So that's why most time we have to talk about alkanes first. So alkanes that we already know is another homologous family. That like we call it the simplest homologous family. All right, so what are the things that you need to take note of in these alkanes? The general molecular formula, this is CnH2n plus 2. What are the other things that you need to take home from these alkanes? Number one, they are saturated hydrocarbon. What do I mean by saturated hydrocarbon? Take a look at these organic compounds. You can see all the carbon atoms are linked together by a single covalent bond. Because they are linked together by a single covalent bond, that is actually what makes it saturated. Now, what does this saturation property make them behave? Now, what happens here? They now become unreactive. So they become unreactive. You know, somebody when you are filled after you've eaten one big bowl of rice and you are all right. You know, those guys they say, I don't do okay. you know. So when you have eaten enough, you are saturated. So here all the carbon atoms are bonded to different atoms covalently. So with a single. All right, so that is by the way. Then we also have another thing we need to look at, the hybridization. What I mean by the hybridization is the type of orbitals that are involved in this single carbon to carbon bonding. The type of orbitals that are involved in this single carbon to carbon bonding. So we have for alkanes, we have one of the s orbital and three of the p orbitals. I would have loved to show this um, hybridization in alkanes, but I'm going to come to it. Now remember, let me take a little bit to carbon. Carbon, the atomic number, the atomic number of carbon is 6. Carbon is number 6. Okay, so then you have to write the electronic configuration. You do 1s2, then you have 2. Let me just use a dot to separate it. You have 2s2, then you have 2p2. Okay, so that is the electronic configuration of carbon. Now, that is obviously very true. But one other thing that I want us to take a look, that p orbital. Remember that p orbital has 2px. So the x, they have 2px, 2py, 2py, and 2pz, because the orbital, the s orbital, remember in SS1 you used to talk about it having a dumbbell shape. So in this case, so the electrons are now distributed into, since we have 2 electrons there, 2p will take 1, another 2p will take 1. So this other electron, there's no electron in the, thank you. There's there's no electron in the pz orbital. So that orbital, so when there is bonding between two carbon, so this other carbon will bring its own, there will be a promotion of electron of these two s orbital. So what we now have here, we now have 1s2, then we now have 2s1. So 2s1, there will be a promotion of the electron from this 2s1 to 2pz1. So that is the excited state electronic configuration for carbon. This is where this is the orbital for carbon that we use in bonding. During this bonding process, if carbon is combining with another carbon, so you have one of the s orbital and 3 of the p's. That is where we talk about the sp3. So that is where we got that sp3 from. So when the carbon and the carbon is bonding, so it uses one of the s orbital and 3 of the p's. So that's where we have this hybrid orbital. So it is this hybrid orbital that they will now use to bond with hydrogen, with other carbon atoms. Okay, so in alkanes, we have it as sp3. In alkenes, we have it as sp2. In alkynes, we have it as sp. Now, if you have any question with this bonding, please you can send the questions on chat so that you don't have to be lost. You must not be lost in this class, because if you are lost, you have always been lost. So that's why you have to be found in this class. So my job is to make sure that you understand this chemistry. Okay, so let's take a look at this alkane, the first member of the alkane series. Now, one other thing you need to take note of, why I could asking you funny question. They try to ask you um what will you say about the bonding. Um, okay, let me get it. When we talk about the physical nature of the alkanes, the the things you need to know here is that the first four members, alkanes, alkynes. Okay, the first four members: methane, ethane, propane, butane. The first four members are usually um, gases at room temperature. So because they are usually gases, they usually have low boiling point. So the reason why they have low boiling point: number one, they contain covalent bonds, and number two, there is bond, weak van der Waals forces between the carbon to carbon molecules. Okay, I think I have that explanation in the next slide. But here you can see the boiling point of methane minus 164 is very, very low. Then now you have a deviation for ethane. I'm going to try and explain this reason why we're having this ethane gain a bit lower. Then we have um, propane minus 42, butane minus 0.5. So as you go higher, the first four members are gases, the next five are liquids, then higher members are solids. Right, so I'm going to talk about this. So you can see the physical properties such as melting points, densities, boiling point increase steadily. This is why question. And the reason why there's an increase is because there is increase in molecular mass. That's the simplest answer you can think of. If you cannot remember van der Waals forces, you can always, just by observing this, you can see that the molecular mass is increasing. You have 16, 30, 44, 58, keeps increasing by 14. I hope you remember what we did last time. The other thing you also need to talk about is that as the number of carbon atom increases, their number of structural isomers also increase. Remember we talked about isomers about that in alkanes, isomerism. So we said the first three members cannot have isomers. So four, the first four, that's methane, ethane, propane cannot have isomers. But when you get to butane, they can have isomers. So it keeps increasing. So you give yourself another challenge. Like I told us in the last time, our students who try to get the 75 possible isomers of decane. It's a good challenge actually. If you can do it, send it to me. We'll archive it. It makes sense. So you become one of my history makers. All right. So the next thing is what we do here is that we take a representative member in our previous lesson. We talked about homologous series, and we talk about the properties of homologous family. So we said that they have general method of preparation, they have general molecular formula, the physical properties uh, begin to vary as number of carbon atom increases. So if I talk about methane, it is expected of you that if you get to the exam and WAEC asks you about ethane, you remember that they are a homologous series and you can talk about it by just using the same technique. Let's take for example, look at this source now. This is ethanoate. Ethanoate. So this is ethanoate. So what do I have here? Ethanoate is what I use to get methane. That means we use two carbon from enoate from an ester or from a salt to get one carbon hydrocarbon. So if you want to get ethane, so instead of using ethanoate, you now use propa. Propa means there are three carbon. Ether means there are two carbon atoms. So it's just for you to think about it. Let me, for those of us who are more curious, let me just show you what I mean by that because it's a homologous series. So I have CH, okay, let me say C2, H5, COONA. So you can see here that there's a derivation here. I can derive C to H6. So by the time I combine it with sodium hydroxide, so obviously my product should be C2H6 plus Na2CO3. It's still the same because it's a homologous series, the same method of preparation. So we use, instead of methyl here, we now use ethyl. You can see we maintain the functional group. So we now use, so that is what we mean by it being a homologous family. Okay. All right. So I can have one question. Somebody, okay, let's see the first question for today. So does soda lime have a molecular formula? Thank you. Now, what actually happened here is that if you should use sodium hydroxide directly, it's it is high, is deliquescent, so it will absorb moisture from the atmosphere and it becomes a liquid, or we can say hygroscopic. But now, instead of using directly sodium hydroxide, we'll use a mixture. This time around, sodium hydroxide and calcium oxide is a mixture. So remember, in SS1, mixtures cannot be represented by a chemical formula. Like impure sand, now you cannot use impure sand to, can't write the formula for impure sand or impure water. Okay, so or your blood, you can't use a chemical formula because it's a mixture. So you cannot use a chemical formula to write soda lime. Even though you know what actually happened here, why would I use sodium hydroxide in case? Because sodium hydroxide is the active ingredient. So during this whole process, care must be taken during the heating process. So you have to heat. I think I have a video on the. Let me see. I have a video on this laboratory preparation. Yeah, so let's look at the a small video on this laboratory preparation.
Preparation of methane. The apparatus used in the preparation of methane is shown on the frame. In the preparation of methane, firstly, sodium salt of monocarboxylic acid is heated with soda lime, a mixture of NaOH and CaO in the ratio of 3:1 at about 630 K. In this process, methane is formed. In this reaction, a molecule of CO2 is removed from carboxylic acid, and therefore the reaction is also called decarboxylation. The methane gas, so formed, is passed through a delivery tube, as shown through the animation, and is collected by downward displacement of water.
Okay, so that is totally fantastic, and that is what we talk about laboratory preparation of methane. So basically, you've seen the whole process. One thing we need to talk, the reason, one why question I've seen in the past is, what is the reason for using soda lime instead of sodium hydroxide? Number one, as I have it in the previous slide, soda lime is not deliquescent and it does not attack glass. So this whole process may lead, if you use sodium hydroxide may attack glass only. So to reduce it, and this reaction also has to be on controlled heating. So you don't just heat this mixture directly, okay? Right, so let's move forward. So some physical properties of um, sodium hydroxide. If you have any question from the video or from the notes, don't forget to always ask your question. All right, so it's colorless and odorless gas, less dense than air, slightly soluble, and is a neutral gas. Okay, is there anything I need to point out? Learn the laboratory preparation, the diagram. Okay, so let's talk about the next thing we want us to talk about is the chemical properties. Remember, I told you that these alkanes are saturated. So when they are saturated, they are chemically inert. They are chemically inert and they are reactive. So one of so a few of their reactions are actually what we have. These alkanes are very, very useful, but let's look at some of their few reactions. The first one here is combustion. Because it is a hydrocarbon, it can easily burn. Like the butane you have at home is a hydrocarbon, so it can undergo burning. So when it burns, it liberates carbon dioxide and oxygen. Okay, so ensure that you learn how to write the balanced chemical equation, and this reaction is exothermic. Okay, so now there are two types of burning. One in excess supply of air, and the second one is in limited supply of air. So when it is in excess supply of air, you get carbon dioxide and water. But if it is in limited supply of air, you don't get carbon dioxide. Although carbon dioxide is unstable, you will get carbon two oxide. Carbon two oxide is unstable, so when it's exposed to air, it automatically changes to carbon dioxide. But the major product here is carbon two oxide. Now, there's one unique product that is common to both of them, apart from water, is a residue of coke. I think that was 2017 or WAEC question or 2018. WAEC asked the question that states the product from when methane burns in limited supply of air. So you have carbon dioxide, coke, and water. Okay, so if it is in excess supply, we have carbon dioxide and water. Okay, now yes, I had to use this question, get this concept clearly for us. Now, the next and most important reaction that alkanes undergo that you need to know for the purpose of WAEC is this substitution reaction. This reaction is unique to alkanes. What do I mean by substitution? Here, during the substitution, the the formula for methane, let's use for example methane, that's CH4 here. So methane here, all the hydrogen atoms will have to undergo substitution reaction. Will have to undergo substitution. What do I mean by substitution? Replacement by another atom. So here we have chlorine replacing the hydrogen atoms. But for the purpose of WAEC, in recent times, I've seen this question. This reaction has a mechanism that follows 3 steps. I had to purposely bring her for students who have been taught by me. Perhaps while we were doing it, we never talked about their mechanism, but in recent times, WAEC has requested that we talk about their mechanism. So the mechanism of this substitution reaction is in 3 steps. The first one is called the initiation step. Second one is the propagation, and the third one is the termination. Now, take note, this reaction can only take place in the presence of ultraviolet light, which acts as a catalyst. The light is acting as a catalyst. So without the presence of this light, it's this reaction is a very, very slow reaction. Now, what actually happens is that in the initiation stage, call it, there's going to be what we call homolytic fission. Homolytic. Let me write the word homolytic. Homolytic fission. In homolytic fission, we see what we call the splitting of a molecule to give the same type of free radical. Like in this case, we have Cl2, chlorine gas, in the presence of ultraviolet light, splits into chlorine radicals, 2 chlorine radicals. So here, this is what we call homolytic. So we have another type of fission that is not homolytic, we call it heterolytic. Check 2013 WAEC past question. You have heterolytic fission. So under heterolytic fission, you see, let's say for example, HCl. HCl can split to hydrogen and chlorine. So in this case, because the chlorine is more electronegative, so the chlorine can go with the electron, while hydrogen will not have any electron. So the splitting does not produce the same type of radicals. So when the splitting brings about the same type of radicals, we call it homolytic fission. But if the splitting does not produce the same type of radical, or it produces different types of radicals, we call it homolytic fission. So in the initiation stage of this reaction, that's where we have the homolytic fission. Then in the propagation, the free radicals, this chlorine ion now attacks, that's what we call it, it will attack this methane because of the heat at which is coming. It will attack the methane, forming a new radical. So you see, you have a methane radical and hydrogen chloride. There are two possible reactions in this propagation stage. In the second type of possible reaction is after the methyl radical has been formed, the methyl radical can either decide to combine with the chlorine and eliminate another chlorine radical, which is the second chlorine, or it will proceed to the termination. When you mean termination, that is the ending. Initiation is beginning, propagation, the steps it will follow, and termination, the result, the end of the reaction. So there are two things that can lead, three things that three termination points. The first one is the chlorine radicals joining together to form another chlorine. Another thing is the methyl radical joining together to form ethane. And another possible product is that the methyl radical combining with the chlorine radical to form the chlorinated alkane. So, but most of the time, what we teach you for Nigerian students, what we teach you is the final product. We don't stress you with mechanism, but here WAEC is asking for mechanism now. So that's how to take a look at it. So here, the main now what are the chances of each of these things occurring is that the last possible product here, where you have the chloromethane, has the highest possibility of occurring. So since it has the highest possibility of occurring, that is why in Nigerian curriculum, uh, we don't stress ourselves talking about producing ethane from chlorination of methane. So here is the things that we usually produce. So the reaction continues subsequently as we subject the whole process to ultraviolet light. Okay, so you can see this, a summary of the reaction. Here, I'm only focusing on the major product, which is the chloromethane. So here you have chlorine combining with methane to form chloromethane, giving us a hydrogen chloride as a byproduct. Take note of that too. We can get a question where I could ask you what is the major product, what is the byproduct. The major product in this first stage of this chlorination is chloromethane, while the byproduct is what? Hydrogen chloride. Subsequent, if you combine the chloromethane with more chlorine radicals, it will give you dichloromethane. Also, you can give you trichloromethane and also tetrachloromethane. You can get to learn all these chloromethane. One of the things that is unique about these chlorinated alkanes is that they are they are all liquids. They are used as solvents. They are used as solvent. Okay, so what do we use as solvent? Solvent is a liquid that you use to dissolve other compounds. So chloromethane, like DCM, dichloromethane, is a very good um, solvent, okay, for organic compounds. Okay, so here are some few uses of alkanes that you must hold on to. Is there anyone that you need to take a look at? Yes. Take a look at the second one. Is used in production of water gas. Methane is used in production of water gas, which is one of the laboratory method of producing method of producing hydrogen gas. Also, we can also say trichloromethane. You only see this question in JAMB, and you also see it in WAEC. What do we use it for? We use it as an anesthetic. The 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 drug that or injection that they usually give to people whenever they want to carry out surgical operation, so they will pass out for a certain period of time. So that is it. Trichloromethane can also be used as an anesthetic in surgical operations, and of course, the trichloromethane is used as a very good organic solvent. So, gentlemen and ladies, that is for alkenes. That's for alkenes. We move forward and talk about alkenes. Like I told you, these are lessons we do not have the luxury of time um, to be keeping tabs on one particular topic. So we'll quickly move on to alkenes. If you have any question on alkenes, drop it. So alkenes, the second homologous series, they are unsaturated. I told you earlier on that alkanes are saturated, alkenes are unsaturated. So the next question is, how do we treat these um, saturated hydrocarbons? we have treated that saturated hydrocarbons, showing us that they undergo combustion, because combustion means burning, and they also undergo substitution reaction. But for alkenes, unsaturated means that they do not have enough single bonds. They do not have enough single bond, so now they have a double bond. So it, that the presence of that double bond makes them unsaturated. So remember, it must it must have a double bond. You can see the last statement there. I talked about the hybridization. It is sp2. The hybridization, the orbitals that join together in the formation of that double bond is 1s and 2p orbitals respectively. Okay, so here are some few alkenes. Take note of the way we draw them. First thing is the first member is ethene, because there must be a double bond between two carbons. So since we cannot have a double bond where we have only one carbon, so you need two carbon atoms to form the simplest member of the alkenes, and that is ethene. Ethene happens to be one of the most important alkene. Is used to carry out a lot of industrial activities. Ripening of fruits. We also use it to make plastics. So it's a very useful organic compound. We use it in making PVC pipe and not the rest of them. Okay, somebody I have a question. Let me see. What's the question? Sorry, what is the hybridization of alkane? sp3. Alkanes have an sp3 hybridization, while alkenes have sp2. sp2 for an alkene. So we have sp3 for alkanes. Okay, so that's the question somebody sent to me. All right, so they have sp for alkyne. So when we get there, we get to understand more. All right, so you can see here the same technique, the same flow. First 4 members gases, next 5 members liquids, higher members are solid. Which one is WAEC interested in? First, let's say first 5 members. That's what WAEC could be interested in. In my recent research, WAEC I've not even gone beyond butene. So, but there's no big deal. Just take note of their general molecular formula, CnH2n. Okay, so I think I told you it's one of the most important members. So that's why we have to study the laboratory preparation. Remember, if you get an exam condition and WAEC asks you to describe the industrial preparation, all hydrocarbons have the same form of industrial preparation, which is cracking of petroleum. We don't have to say cracking of petroleum. You can say cracking of heavy oil. When you crack heavy oils, you get all these alkanes. But if you want to obtain the heavy oils, you do fractional distillation. So that is one way. So cracking is one way of producing alkanes, and alkynes. Okay. So here, but in the lab, we have this laboratory preparation for alkanes. I think I have okay. All right. So yes, we call it dehydration reaction. Under dehydration reaction, dehydration means removal of water. So if you remove, let's say for example, look at this formula, C2H5OH. Remove the formula H2O, subtract it from this. What will it be? How many C will be left? We'll still be left with 2C, but we'll only be left with 4H because we have already removed 2H and 1O. You can see. So that's what we call dehydration. Yes, thank you for annotating. Thank you. Thank you. But so that is what we are talking about. So this is the ethene molecule, and this is another byproduct water. But in WAEC, those guys, I don't want to say it's not WAEC that is wicked, but the chemistry group, they are usually very, very funny people. So they will now ask you, what is the reaction condition? See, number one, the condition for this reaction to take place is there must be presence of concentrated tetrahydrosulfate 6 acid. If you write dilute, you are wrong. Sometimes I think I've seen in the past somebody will write H2SO4 without writing the concentrated. Sometimes they pardon it, but sometimes they don't pardon. So please ensure that the keyword they concentrated. So that is the only way the reaction can take place. Then you have to heat it, and so the reaction is in two ways. So first of all, you get a side product. We call it an intermediate. This is what we call ethyl. The first product is ethyl hydrogen tetraoxosulfate sulfate 6. All right, so that is the name of this first side product here. So if you subject it to further acid, then you have what? The H2SO4 discharge again, and ethene produced. Now, sometimes look at what I said, the mixture of ethanol and excess HCl. So this is usually in the ratio of 1:2. 1:2, that's the ratio of the ethanol and H2SO4. Okay, so that is very important for us to take note of. All right, so I'll move forward and show you the pictorial representation. All right, so this is the diagram for the whole process. So remember, you have to label correctly. You heat the you put an empty flask. The reason for this empty flask, I've seen it in wire question, I've seen it in jam question, is to prevent this reaction. Instead of putting it into the sodium hydroxide, you put an empty flask so that the does not suck back. The pressure of the gas does not allow the sodium hydroxide to be sucked into the reaction container. Does not allow the sodium hydroxide to be sucked into the reaction container. So that is what actually happened there. So we have to put an empty flask. Then we also have to put the sodium hydroxide here as a purifier to remove gaseous impurities. And what are those impurities? Carbon dioxide and phosphine. The formula for phosphine is pH3. Okay. All right. So we have 2 minutes for the end of this session. So that, remember, this is a 1-hour chemistry lesson. So in the next 2 minutes, I will encourage you. I will log us out and you log in again so that we will be able to complete our lesson till 4 o'clock. Okay. Right. So no problem. Yeah. So let's continue. So I've explained this. The function of putting this empty flask is to prevent this sodium hydroxide from sucking into to suck back into the reaction mixture. Then also we have to put the sodium hydroxide to remove gaseous impurities, mainly carbon dioxide and phosphine. All right, so you can talk about some unique properties of alkenes. Very, very unique, colorless, with a faint sweety smell, sparingly soluble in water, and less dense than air. All right, very great. Okay, so we'll move forward. Chemical properties of ethene. Now, so ethene, like I said, ethene, like I told us earlier on, is highly unsaturated. Being unsaturated means that it becomes quite reactive. So it's very reactive. So unlike alkanes only undergo substitution reaction and combustion. Alkanes undergo a whole lot of reactions, mainly addition reactions. We call them addition reactions. Then we also have oxidation. Then we have polymerization. So in summary, this chart shows all the possible reactions of ethene. Now, let's start. What we are going to do, we'll log out now and come back and finish up this thing. We are good to go. Make sure that you log in back, okay?